Case Study: Hazard Characterization in Vat Polymerization. This case study provides an overview of the additive manufacturing technique known as vat polymerization, or vat photopolymerization, a process in which a photosensitive resin is cured in a vat, one layer at a time. The learning objectives for this module are to describe the process steps that make up vat polymerization, identify the hazards that may be present during those tasks, and identify exposure controls that may be effectively used for those tasks. Vat photopolymerization, or VPP, uses photosensitive polymer liquids or resins that cure when exposed to light, resulting in a solid part. The light source for this printing method is usually either a laser or an array of ultraviolet light-emitting diodes, or LEDs. There are a lot of different types of liquid resins used to achieve the desired qualities in the finished parts, whether that's a surface finish or a particular texture, or degrees of flexibility or rigidity, or biocompatibility. These characteristics depend upon the chemical makeup of the resins used. VPP can be used for prototyping, tooling, and final part production, depending upon what the part is. Prototyping was one of the earliest applications for additive manufacturing. The generation of cosmetic and presentation models and visual aids can speed up the design process for an object significantly. A printed representation can communicate design intent, clarify ambiguities, and generally communicate a concept efficiently and effectively. Functional prototypes as well can be used to test form, fit, and function. One of the major uses of VPP technology is for dental prosthetics, where fit is crucially important. Functional prototypes can help to validate designs and identify issues with tolerance, fit, alignment, and function before the final parts are manufactured. This can save a lot of redesign time, tooling costs, and materials. The VPP process is ideal for creating highly accurate parts with fine details and smooth surface finishes. It's used extensively in the medical and dental fields, where it's used to create tools for training surgeons, facial prosthetics, and hearing aids. It allows for quick generation of parts or products that require fine detail, intricate customization, and smooth finishes quickly. Here's a representation of the VPP process. A resin is obtained from a vendor. Depending on the product, that resin might be mixed with other materials or portioned out to different containers or be used right out of the container. Next, the vat part of the printer is filled with liquid resin, and the printer is programmed with the design for the final part. Once the process is activated, it prints the part from the design. The light activator is applied selectively to the build platform inside the resin vat, curing one ultra-thin layer at a time and solidifying only those portions of the resin that will become the printed product. At some point early in the build, the operator may pause the build and check that it has begun correctly and that the build is adhering to the platform and that nothing appears off. Then the printing proceeds. Once the print has been completed, the cured part is submerged in a vat of resin. It must be removed from the build platform. This process is usually done by hand, and it may require scraping with a tool depending on how tightly the part is adhered to the platform. At this stage in the process, although the part itself is mostly cured, it is still covered in uncured liquid resin from being submerged in the vat. The parts are usually wiped off by hand before receiving more intensive cleaning in a parts washer of some kind. Once the uncured resin has been removed from the part itself is placed into a separate UV curing module to make sure that the resin is fully inert before proceeding. After that is finished, the part can have any support materials removed and any final sanding, smoothing, or painting that may be needed. Vat polymerization materials vary by process and by what is desired from the final part, but they are all light-reactive thermoset materials in which the molecules bind together and become solid when exposed to certain wavelengths of light. Feedstock materials for vat polymerization include thermoset resins, solvents for cleaning, and any additives that might be present in the resin mix. The resin or solvent vapors or thermal degradation products that have been generated from the heated resin mix can be inhaled if the worker is exposed to contaminated air. There is also the potential for dermal exposure from contact with surfaces that are contaminated with the materials. VPP technology does pose hazards to users, which both operators and EHS personnel should be aware of. First of all, the primary materials used for the process are photosensitive resins, many of which are dermal sensitizers. This means that they can cause allergic skin reactions in exposed workers, and after the first sensitization, the reactions can be triggered at exposures far lower than any applicable exposure limit. Workers should avoid both inhalation and dermal contact with these materials. This can be tricky from an inhalation standpoint because the vapor pressures of the resins may vary significantly, and it's tricky from the dermal contact standpoint because many of the resins are clear or transparent, which makes them difficult to identify on surfaces. And while a spill of resin will eventually fully polymerize and become inert in ambient lighting, there's no good way to tell how long it stays volatile and how long it remains a dermal hazard. Inhalation of volatile organic compounds, or VOCs, is another hazard to be aware of with this technology, and is applicable to both the printing step and the post-processing step in which solvents are used to remove uncured resin from the part. Typically, the post-processing equipment uses a much larger volume of solvent than would be in the resin. The last hazard to be aware of is the potential for UV exposure, either from the printer or from a post-process UV curing module. Generally speaking, the printers contain interlocks to prevent operation of the light source with the cover open, and this provides adequate protection from UV during the printing. Post-processing UV curing modules are also usually fully enclosed when operated correctly. Now I would like to break down the process task by task and look at some monitoring data based on one workplace's process. The first task we'll look at is resin handling, which includes both filling the vat with resin at the beginning of the process and emptying it or reclaiming it at the end. The materials come in bottles or jugs. For some printer models, they might come in cartridges, which can be installed directly into the printer without having to pour the resin from one container to another. But with this type, the resin tray had to be filled. Additionally, in an R&D setting, sometimes various additives were being added to the resin, which required a mixing step. For that, both the resin and the additive would be weighed into a separate container like a beaker or an open-mouth jar, stirred manually, and then transferred to the resin vat. At the end of the process, after removing the finished part and the build platform, the resin tray would usually be covered with foil and carefully stored in a chemical storage cupboard until the next time it was needed. You can see from the picture the various types of containers that are used to pour resins from. Integrated personal air samples during resin handling tasks revealed air exposure levels well below the relevant exposure limits. Note the logarithmic scale of the y-axis on the graphs above. The red dots are samples that came back below detection limits, with the red dot located at that particular sample's detection limit concentration. This particular set of resins had extremely low vapor pressures, so it makes sense that such low volatility materials would not have high inhalation potential exposures. The next task we'll look at is the printing process itself. Printing doesn't really involve any interaction on the part of the operator, except for one event partway into the build when the operator will pause the print and check that the initial build layers are adhering to the build platform properly. This may or may not involve opening the cover of the printer to examine the build, but it should not include any touching of the print or of the liquid resin. Integrated personal air samples collected during the printing task also showed levels of monomer resin far below any relevant OELs. Note the logarithmic scales on the y-axis again. In addition, the variability was quite low, suggesting that with these resins and this type of printer, low air exposures could be safely predicted. The operators stayed in the vicinity of the printer during the printing tasks, usually within 5 to 10 feet from the printer. The last set of tasks we'll look at are the post-processing tasks. These include removing the build tray from the printer at the end of the run, removing the part from the build platform, wiping the excess uncured resin off of the part and the tool used to pry it from the platform, and washing the part in a parts washer. This also includes cleaning the equipment such as the build platform after the run. Once the build is finished, the build platform is removed from the printer and the parts removed from it. This typically involves scraping with razor blades or other implements and lots of direct contact with the uncured resin. You can see in the picture here the researcher using a matte knife to remove the part from the platform. This video shows part of this process. Next, the parts are washed, either by rinsing them by hand in a container of solvent, by machine in something like a centrifuge or an ultrasonic solvent bath, or both, prior to post-process curing in a separate UV curing module. Rinsing them by hand obviously involves a greater potential for exposure, but with either method, the parts must be handled to put them into the wash. After the parts were washed and placed in the UV curing unit, the cleaning tasks were done. The researcher used a razor blade to remove the excess resin from the platform. Isopropyl alcohol was used as a solvent to clean the platform, the knife, and the laboratory bench afterwards. The contaminated paper towels were then disposed of in hazardous waste. Two main components of the printer itself that require regular cleaning are the build tray, which holds the liquid resin, and the build platform, which the parts are built on and adhered to as the print proceeds. At this workplace, as was mentioned earlier, the build trays were stored with the resin still in them and reused several times before being emptied and cleaned in the parts washer. The build platform, however, had to be cleaned after every run. In this video, you can see the researcher working to clean the build platform. Integrated personal air sampling for post-processing tasks similarly showed levels of the resin below method detection limits, and for this process there was greater variability. This makes sense because these are the tasks with the most variation. A lot depends on how difficult the part is to remove, how difficult it is to remove the excess resin, how the part is wiped off, and whether there were any spills on the work surface to be cleaned, and other similar concerns. That the levels were still quite low is consistent with the low vapor pressure of the resins. I would like to offer a supplement to the integrated personal samples shown here. Simultaneously, particulate data was collected during the process using real-time detection instruments placed on the bench beside the printer. These instruments were able to detect particles with aerodynamic diameters between 10 nanometers and 20 microns. You can see by the graph shown here that although the integrated samples revealed air concentrations that were very, very low, there were still particles being emitted, and those particles were almost entirely very, very small. You can see here by a different grouping of the data with the nanoparticle data added in, the concentrations of nanoparticles were anywhere from 1 to 4 orders of magnitude higher than the particles in the 1 to 20 micron range. Here again, I had to use a log scale on the y-axis to make the concentrations of larger particles show up on the graph at all. What this means is that this process does emit nanoparticles during all tasks. Analysis by Stefaniak et al. Performed for a similar process showed a wide array of substances making up the nanoparticles due to partial degradation of the resins and the additives. We still don't have a widely accepted exposure limit to pertain to nanomaterials, even if their makeup was identical, so it's difficult, if not impossible, to state what exposure level is safe or not. More research needs to be done in this area to fully characterize these inhalation exposures. The other type of exposure concern with these resins is dermal exposure. Because they are so often dermal sensitizers, it's important to minimize the potential skin exposure to them and, if possible, to prevent it entirely. Because of certain additives these researchers had habitually mixed into their resins, the resins fluoresced under blacklight. This provided us with qualitative evidence that over the years there had been many spills of the material, either not cleaned up or insufficiently cleaned. The resins, as I mentioned earlier, are clear, and it's difficult to detect a spill or other surface contamination. In addition, it's unknown how long any given resin might take to polymerize or cure under ambient laboratory lighting, so there would be no way to know how long a spill was potentially hazardous. Surface wipe sampling performed in the lab showed several non-detects, but a few contaminated spots that exceeded the internal surface limit, and visually there was no difference between the perceived contamination of the non-detects versus the hits. Here's an example of the difficulty of detecting surface contamination by sensitizing resins during VPP work. The paper towel, bench surface, and tweezers in the picture on the left look clean. But shown under blacklight, we can see several hot spots of contamination. Unfortunately, detection using the blacklight is not a permanent or fully effective detection method because not all resins have fluorescing additives mixed in. That we can see it under blacklight here is because of the additive, not the resin itself. The results for air exposure measurements taken for this process were uniformly low. This was partially due to the low volatility of the resins, but also to the fact that the laboratory had 9 air changes per hour of general exhaust, as well as a dedicated local exhaust ventilation hood positioned over the printer. With the persisting unknowns about the risk associated with this process, particularly the nanoparticle emissions, ventilation is the best control that can be used to mitigate air exposure. There aren't really any good alternatives. There are different ways that ventilation can be implemented. Sometimes it's possible to put the printer in a fume hood. Sometimes local exhaust is available. Sometimes direct ventilation to the outside is possible. Sometimes a ventilated enclosure can be built. There may even be a high enough general exhaust ventilation to prevent hazardous exposure levels, depending on the materials and the work environment. But there isn't really a way to get around the necessity for some form of ventilation. To prevent dermal contamination, there's not as directly obvious an engineering control solution. It's probably necessary to have a program for preventing surface contamination by sensitizers, with a standard operating procedure that workers can be trained on. Every step that can be done to minimize exposure can help. Use of the proper PPE is a given, of course, but it should not be the extent of the program. Hygienists should work with employees to develop work procedures that minimize the chances for spills, drips, or other contamination. Is it possible to use only resins that come in a cartridge that's inserted directly into the printer? That would eliminate the need to mix and pour. Can the workspace be close to the hazardous waste containers so that the cleaning materials and excess resins don't have far to travel to be disposed of, particularly without a door in between? If it's possible to put the printer in a fume hood, can the entire process be contained in the fume hood to control potential contamination spread? What cleaning procedures should be developed and implemented? It may even be possible in some circumstances to use disposable covers on the work surfaces that can be disposed of at the end of a run or a shift. Very likely, your contamination prevention program will be a mixture of engineering controls, administrative controls, and personal protective equipment. It will take participation by all involved workers to make it successful. To sum up, let's take another look at the original learning objectives for the case study. We described and demonstrated the tasks that make up the VPP process, identified the potential hazards during each of those tasks, and we discussed the exposure controls that can be used for them. I hope this case study broadened your understanding of the vat photopolymerization process in additive manufacturing. Thanks for watching.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program. a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.